else?
Yep.
I got the rest of them down here.
Yep, he can hear probably most everything.
Okay, so section 4.1. This is, like I said, a real quick one. We good? Matching simple graphs with situations. All right, so you're going to be given a situation. It's common sense. Okay, a little bit. You're going to have to evaluate a couple things, but for the most part, you'll be able to, take out the clues from the description, figure out the graph. All right, so you got that at the top. It says each day several leaves fall from a tree. One day a gust of wind blows off many leaves. Eventually there are no more leaves in the tree. Choose the graph that best represents the situation. So you got to understand, so this is the number of leaves. What does it mean to be increasing? What does it mean to be constant? What does it mean to be going down? So if it's increasing, what's actually happening to the number of leaves? It's getting bigger. So somehow more leaves are showing up. If it's constant, it means the leaves are exactly the same. And then if it's going down, that means it's losing leaves. Well, which one, if you take a look at those, saying, which one do you think would match the description?
Graph B.
Graph B, because it's losing leaves, and then here's losing them faster because that's when the wind comes. And then it says it's going to lose all of the leaves. That means it has to go down to 0. So that makes sense. At no point is the leaves constant. It's always losing. So use the context clues with the graphs. All you got to do is circle that one in the middle. That's it. Air temperature. Increase steadily. Okay, increase steadily for several hours, then remain constant. At the end of the day, the temperature increased slightly before dropping sharply. Choose a graph that best represents the situation.
Graph C.
Graph C. Okay, typically, like increase steadily would mean like a line going up. Okay, not like a jagged or just not all over the place. So that kind of means, and then these two kind of right there, they discount themselves because this would be a steady from the beginning. So usually you can figure out what doesn't work as well as figure out what does work. Okay, so we got graphs that are called continuous, graphs that are called discrete. Like a continuous graph is something you can measure at all times. So like your temperature. So like we could keep a probe on you, like if you're in the hospital, they keep a probe on you. Like though your temperature is there the whole time. Your heart rate, they could measure at all moments. Okay? Your pulse, they could measure. That would be continuous. The amount of money in your pocket, that is not continuous because that fluctuates over time like every day. Okay, that would be something that would be discrete, okay, for that. So there is a difference between that. The number of people in the class each day would be discrete, okay, because you can't measure it at any moment. Your temperature, boom, we can take it, okay, it is going to be different, than the previous moment. Theme park attendance would be distinct, okay, theme park attendance would be distinct. All right, I don't think this one is on, wait, is this one on the bookstore one? Nope, just pay attention to this. It says, sketch a graph of the situation, tell whether the graph is continuous or discrete. All right, a small bookstore sold between 5 and 8 books each day for 7 days. Is that continuous? Is that like temperature? Is that like heart rate, something that you can measure any moment, okay? Or is that something that you measure once at a time, okay? So continuous versus discrete. Preston, am I making sense?
Yes, but you're going to start recording.
I did. I did. So would you say that situation is continuous or discrete?
Discrete.
Discrete, because it's not like a temperature. It's not like a heart rate. So in that case here, and this is just a situation, for instance. So this is the number of books sold. You can't say how many books did you sell after 3.5 days. It's got to be 3 days, 4 days, and 5 days. So that would be a discrete case. You're also going to be able to have to kind of draw a graph given a situation. All right, so let's do this together. It says, Henry begins to drain a water tank by opening a valve. He then opens another valve. What's that gonna cause it to do? Drain faster. Then he closes the first valve, so it's gonna drain a little slower. He leaves the second valve open until the tank is empty. So what's that gonna look like? So I'm gonna tell you, let's say the water level started here. So for the first valve is open, how's that gonna change? The water level is gonna increase or decrease? Okay, Joe? It's gonna decrease, and at a steady rate. So you kind of wanna have a steady line going down. Whoa. Okay, so it wants to be on a steady angle. But what happens once you open up that second valve? Joe? It's gonna go at least fast, probably twice as fast, but we're not gonna teach. So that means it's going to go, you just have to make that steeper. Now there's one more action that happens. Here's your first valve open, here's both valve opens. When we close the other valve, then it's not going to go as fast, right? So it's going to go at a less of an angle. So those are the three things you need. Okay, it's decreasing at a certain rate, then it starts going faster, then it slows down. So you got those three cases. Write a possible situation for this graph over there on the right. And I'll kind of give this to you because the first time is a little bit hard. Here's the speed of something, and let's say it's a car. Here's the speed of a car. And this is just time. First of all, let's figure out what's going on. It is the person's speed decreases, and then what happens here? It's constant, and then what happens here? It slows down to a stop. What would be a situation? Well, I think the easiest way, what do you got, Christian?
A stop sign?
A stop sign, yes, but you have to explain why it goes constant, though. Okay? Why it goes constant. Joe? What's that? The speed limit, okay? To get that, we'd have to maybe give me just a little more characteristics. But think about this. Let's say Mr. Schler's driving on the highway. He's going about 85. He can drive a little fast. You do this thing.
My kids are in the car. So.
No. And then let's say the speed limit is 65. What would cause him to quickly go from 85 to 65?
A cop.
He just passed a cop. So he's going 85, he sees a cop, he's like, oh crap. Slows down to 65, he's gonna go 65 for a little bit, but then why did he just slow down to 0?
He got pulled over.
Yeah, pulled over. Does that make sense?
Deputy McKay got me.
Yeah. So he's going over, somebody's going over the speed limit. You pass a cop, you're like, whoop, all right, I'm gonna go down, and then you just try it and say, all right, I hope they're not coming after me. And so he goes 65 for a while, and then he keeps looking in his rearview mirror, and then all of a sudden he sees the lights. Goes to 0.
Been there.
Okay. So does that make sense? That's section 4.1 in terms of just like looking at a graph and interpreting it. So that is that section. What is it? Oh, 4.2. All right, let me give you the notes to the next one. We are doing good.
4.2.
Yep, I got them over here.
Yeah, we didn't have much. So I guess,
The main part of that first part there, we do that. I got these guys back here and everybody down the side. Amanda, tell me everything you know about the domain of a function. Okay. Would that be nothing? Jay Lee, tell me everything you know about the range of a function. Nothing? Well, I guess we're needed, Mr. Schler.
I think for the first time all year, this is not review stuff.
So we are needed. Allie, what do you know about the domain? Nothing. All right, it's not difficult. It's not difficult, but it says right here, we're gonna identify functions and we're gonna find the domain and range of relations and functions. So we're gonna have to define it and we'll talk about how to figure that out. Okay, now, this first part here, a relation is anything that can be represented by a set of ordered pairs. Let me see what I got there. Let me get one of these, just so I can look.
You
at it.
will see this again. Algebra 2, they love domain and range for some reason. Okay. So it is going to come back. We're going to use it a decent amount through the next couple of sections. So don't learn it today and forget it tomorrow. All right.
Yeah, I mean, and it obviously is with everything, keep a hold of these. But usually we use, Austin.
For like this graphing stuff, is it like, if it's gonna be on our test, are we gonna have to draw the graphs or are they gonna be there for us?
For tests, we'll put the graphs there for you, okay? So you don't have to worry about drawing those out. Okay, usually to generate ordered pairs, we use an equation in math. So I'll say y equals 2x plus 6, and then you'll plug in 2 and you'll get back 10, and that'll be the ordered pair 2, 10. Okay, so that's typically how we do it in math. But there's other ways to come up with relations to generate ordered pairs. Like they talk about the track meet. So in first place, you get 5 points. So that would be the ordered pair 1, 5. If second place, you get 3 points. That would be 2, 3. Third place is 2 points and fourth place is 1. So you still get ordered pairs, but they do it a different way. A lot of times in math, we're just going to say, all right, here's an equation for a certain x value. What do you get for y? So if I plug in -4, 2 times -4 is -8. -8 plus 6 is -2. That would be that ordered pair because it's found out by a different rule. Okay. Well, there are multiple ways to represent relations. Okay. There's 3 of them. Okay, right here. First one is a table. All the x values would go first. Okay, and then all the y values go under y. So this is all you need to have. So that means 2. When I plug in 2, I get 3. When I plug in 4, I get 7. When I plug in 6, I get 8. So just fill that in, or is that already filled in for you? No, you need to plug it in. Now, that's a table. A graph. You plot those points. Well, what was the first point? It was 2, 3. The next point was 4, 7. And the last point was 6, 8.
This one still have negatives.
What's that?
These ones don't say that they're negatives. So it'll still be the same thing.
No, that's not negative. That's just a positive one. It just is just a line on the graph. The third, you are most familiar with these 2 ways. The one you're least familiar with is what's called a mapping diagram. Okay, on a mapping diagram, so you've got 2 little balloons there. We'll call them balloons. So under the X, we list basically where it was at the table. And then under the Y's, we list the Y values. And you draw an arrow to show where which one the 2 is associated with. So when we plug in 2, we get back 3. Now they're not always going to go straight across. And the first time you're like, well, this really doesn't make sense. But in certain situations, they're going to go to different values. So I got 2 goes to 3, 4 goes to 7, 6 goes to 8. 3 ways to represent a relation: a table, a graph, a mapping diagram. Okay, so maybe we got that. Table, a graph, a map. The one you're least familiar with is the mapping diagram. We'll do a couple as we go through. All right, domain and range. Okay. The domain of a relation is just the set of all first coordinates, typically the x values. That's all it is. Okay. The range of a relation is a set of all second coordinates or y values. Okay. Domain, which x values did I plug in? Range, which y values did I plug in? Okay. It's a little bit easier when you're given a mapping any of those 3 in that order. So take a look here. It says give the domain and range of a relation. So and just pay attention to this. The way this is written or shown, 6 has an arrow to -1. That means that their ordered pair would be 6, -1. Just make sure you understand that. 5 goes to 0, right? And then 2 goes to -4. That would be the ordered pair 2, -4. And 1 goes to 0. All right, so just understand that. All right, now the domain. The first set is always your X values. Now, here's a couple key things. You never repeat numbers, and you put them in order from smallest to biggest. So for domain, out of 6, 5, 2, 1, what's the smallest one? It's 1. So you would list as 1, 2, 5, 6. These numbers are in the domain. And now when you have a set of numbers, like there's only 4 numbers in there, we put those braces around that. We put those braces. What's the range? In what order would I put the range? The range of the Y values that it goes to, and remember there's an arrow on those. The smallest one is -4, then -1, then 0. So that's your range. So domain, they give you this mapping diagram, you just take the first set, put them in order. Don't repeat. Now, even though 5 goes to 0 and 1 goes to 0, you only list the 0 one time. You will not list it twice. Okay. All right, now I got a table. Domain is all the X values. In order, don't repeat numbers. Okay, so my domain. All right, Evan, what would be my domain?
1, 4, and 8.
1, 4, and 8. Range. Oops. Don't repeat numbers. So our range, Joe? 1 and 4. Just 1 and 4. 1 and 4. Okay, that's all we got. So domain is your first coordinates. Your range is your second coordinates. Put them in order. Don't repeat numbers. All right, now.
Remember, how do we write ordered pairs? We're gonna graph them. Is it X comma Y or is it Y comma X? You should know this.
X coming.
X comma Y. Okay, well, if you recognize too, every single time Mr. Dulep has said, referred to these new vocabulary words, domain and range, it's always been domain and range. Not once has he said range and domain. Okay, for whatever reason, we're always gonna say domain and range. Domain comes first, just like your X value comes first on your ordered pair. Okay, range comes second, just like your Y value comes second. And we wanna keep those terms straight in terms of which variable that they're referring to. Okay, domains are first, ranges are second.
All right, now it gets a little tricky, maybe. Do you have a list of ordered pairs? No. We have a graph. We could generate some ordered pairs from here. But here's what you got to remember: domain is which values? Is domain X or Y, Josh? X. All right. What numbers show up on that graph? What X values show up on that graph? Okay, call it.
1 and 5.
1 does right here. Okay, that would be the ordered pair. Hold on. Don't write any of this down right now because we're still figuring this out. That would be the ordered pair 1, 4, right? And this would be the ordered pair 5. Why does it keep going there? 5, 3. Do we agree with that? Are those the only 2 X values that show up on that line? Okay, because 1 is right here and 5 is right there. Okay, Christian, are those the only 2 X values that show up on that line?
Yeah.
What about right here? Is that a point on the line? Is it a point on the line?
Mhm.
Yeah. So what would be that order pair? It would be what? 3 and say 3.5. So that means 3 has to be in the domain. Is this a point on the line? Yeah. What's the X value of that point? It is 2. Is this a point on the line? Yeah. What's the X value there? 4. Are there other points that have other X values? Yeah. Preston, what would be the X value about of that point? 1.5, and then that's 2.5, and that's 3.5, and that's 4.5. Can you give me more?
Yeah.
You-
2.75.
All right, 2.75. How about 2.85? Could we technically list all of them? All of them? No, because it's infinite. All right, so how do I tell the domain? How do I list the domain so I hit all these points? What is the smallest number in the domain? What is the smallest number in the domain? Colin. 1. What's the biggest number in the domain? What is the biggest x value?
5.
Does it hit everything in between? How do we write that? We just did this, compound inequality. 1 is the smallest number, 5 is the biggest number. I need everything in between here. So that means that 1, whoops, is my smallest number. Domain is always x, and there's my biggest number. So that's how you write the domain. So it says every number between.
I got you. And we need to lock this.
All right.
I learned something.
Every number in between fits. Now, let me go backwards. If they just have numbers listed, then we just list 1, 4, and 8. Okay? If they just have right here, 6, 5, 1, 2, we just list those. But if we have a graph, we got to do this. Okay? And now this is the smallest x. This is the smallest x. This is the biggest x. And here's what you're going to do.
Again, this is what we were doing when we were graphing those inequalities, and especially graphing those compound inequalities. So like that back third of your test.
Find the furthest point on the left and find the furthest point on the right. And if it's continuous through there, that right there is your domain. 1 to 5. All right, now let's see, can you apply this to a range? Anybody have an idea what the range would be? You think you can figure it out? It's going to be similar to different numbers though. What's the biggest y or the smallest y value it hits, and what's the biggest y value it hits? Colin?
3 is less than equal to x, which is less than equal to 4.
3. He's right. He is right. 3 is less than. Now here's the only difference though. Put y. Y is your range. Find the lowest point, the smallest y value here on the graph, and find what value it is. And it is 3. And find the biggest one, and it hits everything in between. So I could come up with a point that has a y coordinate of 3.5, or 3.25, or 3.75. You could not give me a point that has a y coordinate of 10 because it doesn't exist there. All right, so this is your domain and range for a graph. All right, look at this one here. Same thing, it's continuous. This is that bottom one here. It starts at -8. It goes around and it ends at +8. Okay, so right there. All right, Rachel. This sinking in yet?
No.
No. What's the smallest x value? The furthest point on the left has an x value of what? What's that?
8.
On the left.
Oh, -8.
-8. You find the furthest point on the left is -8. What is the furthest point on the right? What's its x value? 8. So I find that.
So those are the x values because they're on the x-axis.
Does that graph at least go all the way between those two? Doesn't go straight line, but it goes between it, right? That tells us those are all the x values that show up on the graph. So how do I write it? Go from smallest number, -8, is less than or equal to x is less than or equal to 8. Okay? And this is a one case where you've got to have it exactly down. Like don't not get this down. Get this down exactly as that.
And you're always using less than or equal to on this.
Good. Look at the range. Look at the range. See, and if you think you know it, just kind of mentally tell it to yourself. Mentally tell it to yourself, and then let's figure it out. Morgan, Candle. You think you got the range?
Not really.
Is there a lowest y value? Where's it at? It's actually 2 of them. Right here, correct? And right here. Is there anything below those 2 points? No. So now just go to the y-axis and put a line here. All right. Is there a highest y value? Where at? So right there, that point right there? Okay. Now, does that graph exist everywhere in between there? So this is now, how do I take that and write it in that form? Go from smallest y to biggest y. Smallest y would be what? 0. So start with 0 is less than or equal to y. Make sure you put a y is less than or equal to, what's the biggest one? 5. All right. This is new, so first time you do something new, it takes a couple times, okay? All right, now I know we're getting tight on time. Let's see here. Hey, flip that over on the back. Let's look at this one. We'll have to go over. Yep. Ooh, and let me go back one. You guys see where that one's at? You got that on the back top? All right, what is the domain of that one? Is that a graph? No, it's just a list of numbers. So for this one, how do I list them? Smallest to largest, don't repeat numbers. So the domain would be -8, -4, 4, and 5. You guys go over what's the function? Yeah. And then what's your range? Your range is just 1 and 2. Range is just 1 and 2. And how about that one? Now that's a graph. So this is where it's going to be that less than or equal to part. You have a smallest x anywhere. All right, Josh, take a look at that. What do you think? Take a look at it and see if you can think what the domain would be. 3 smallest x. So that would be 1, 2, 3. Okay, that would actually be the biggest x. Would be 3. What would be the smallest x? Good. So you go this way. 1, 2, 3, 4, right there. So it's going to go from here all the way over to there. So how are we going to write that? -5 is less than or equal to x is less than or equal to 3.
What's up, Colin? What's up?
And how about that range? Whoop. All right. I know we're running out of time. We'll have to finish that, but I do want you to just do a little bit here. Do page 233. Do page 233. Okay. Like the movie.
Yeah.
Okay. 233. Turn that in. Start submitting.
Hey,
Start
do you have
submitting.
a,
I'll submit on my Mac here.
Well, and we're gonna do that Thursday for team meeting.
Okay.
Program meeting, right? Anytime yet?
No.
Yeah.
Oh,
No. That's Friday. That's Thursday.
Oh, the big meeting.
Big meeting.
No, I'm done at 5.
Okay.
And I gotta see if we can do it together. We have to do it separate.
Oh.
So what time is your practice? Why don't you